Look up on a clear night, and you can see a few thousand stars, a smear of the Milky Way, maybe a planet or two. It feels like you are seeing the universe. You're seeing almost none of it. For every gram of ordinary matter in the cosmos, the stuff of stars and planets and people, there are more than 5 grams of something else, something that gives off no light, that we have never held in a detector, and that we still cannot name. We call it dark matter, and this is the story of one strange place it might already be sitting. Inside the recorded data of the largest machine ever built, the Large Hadron Collider. Not out among the galaxies, in a hard drive at CERN near Geneva. We will build up to that idea slowly, one step at a time. The first question is the simplest one. How do you weigh something you cannot see? If a slow, careful walk through the universe is your kind of thing, take a moment to subscribe and we will keep going. Picture yourself standing in a field far from any city on a clear and moonless night. The sky above you is crowded with light, a few thousand stars if your eyes are sharp. The soft band of the Milky Way arching overhead. It looks full. It looks like everything there is. Here is the plain fact that took astronomers most of a century to accept. Almost all of that light comes from a thin skin of the universe. The stars you see, the gas between them, the planets, the dust, every glowing thing your telescopes can reach, adds up to about 1 part in 20 of what is actually out there. The rest gives off no light at all. It does not shine. It does not glow. It does not block the light behind it. It simply has weight. We call this unseen stuff dark matter, and the word dark is doing careful work. It does not mean black, like a cloud of soot. A cloud of soot would still swallow the starlight behind it and throw a shadow. This throws no shadow. Shine a beam through it, and the beam comes out the far side undimmed. Think of a pane of perfectly clean glass in a doorway. You walk toward it and see nothing, no glint, no smudge, until your hand meets something solid. Dark matter is stranger than that glass, because even glass bends the light passing through it, and this does not bend light at all. The one thing it does is pull. That pull is the whole reason we know it is there. Gravity does not care whether a thing shines. A mountain and a cloud of fog with the same mass tug on you with the same force. So when astronomers add up the gravity in the heavens, the bending and the spinning and the falling, they find far more pull than the glowing matter can account for. Something heavy is out there, in vast amounts, holding galaxies together against their own spin, and it tells us nothing about itself except its weight. For every gram of ordinary matter, the kind that makes stars and oceans in your own hands, there are a little more than 5 grams of the dark kind. Turn that around, and it stings. Everything humanity has ever seen, touched, tasted, or measured directly is the smaller share. We are built from the rare stuff. The common stuff, the majority owner of the cosmos, has never once been held. This is not a fringe idea whispered at the edge of science. It sits at the center of how we understand the universe. Every large galaxy we know appears to be wrapped in a great invisible ball of this matter, a halo far bigger and heavier than the bright disk of stars inside it. Our own Milky Way rides in such a halo. This sun, and Earth with it, is moving through a thin fog of dark matter right now, and you feel nothing, because it slips through ordinary matter almost without touching it. That slipperiness is the problem, and the promise both. A thing that barely interacts is a thing that barely leaves a trace. For most of the last century, the only trace we had was gravity, felt across millions of light years, telling us how much is there but never what it is made of. So we are left with a simple, stubborn question, and the rest of this story is the long attempt to answer it. If you cannot see a thing, cannot touch it, cannot catch its light, how do you learn what it is? The honest first step is smaller and more concrete than that. Before you can ask what dark matter is, you have to be sure it exists at all. And the first person to stumble onto the evidence was not looking for it. In 1933, a Swiss astronomer named Fritz Zwicky was studying a great swarm of galaxies called the Coma Cluster. It sits about 300 million light-years away, a loose city of more than 1,000 galaxies bound together by their own gravity, each one a whirl of billions of stars. Zwicky wanted to weigh it. He had a clever way in. Galaxies in a cluster are not still. They drift and swing around one another, pulled by the combined gravity of the whole group. The heavier the cluster, the harder it pulls, and the faster its galaxies must move to keep from flying away. So if you measure how fast the galaxies are moving, you can work backward to how much mass is holding them. It is the same logic as a stone on a string. Spin it slowly and a light string will do. Spin it fast and you need a strong grip, or it tears loose and sails off. Zwicky measured the speeds, using the way light stretches and shifts when a galaxy moves toward or away from us. What he found made no sense. The galaxies in the Coma Cluster were racing around far too fast. At those speeds, the visible matter, all those glowing galaxies added together, came nowhere near enough gravity to hold the swarm. The cluster should have torn itself apart and scattered across the sky long ago. Instead, it was intact, held together as if by a grip that was not there. He did the arithmetic and reached a startling number. To bind the cluster, there had to be something like 400 times more mass than the light revealed. Even with later corrections, that figure came down, the gap never closed. He named the missing ingredient with the German phrase dunkle Materie, dark matter. This was the first time anyone had put that name to the puzzle, backed by a measurement rather than a guess. Zwicky was not a comfortable colleague. He was brilliant and abrasive, quick to insult men he thought were fools, and just as quick to be right about things no one else could see. He proposed neutron stars before there was any evidence for them. He mapped the distribution of galaxies decades ahead of his field, and on dark matter, the most important idea he ever had, the community mostly shrugged and moved on. Part of the reason was fair caution. Weighing a whole cluster from the motions of its galaxies is a delicate business. Maybe his assumptions were off. Maybe the cluster was not settled and calm the way his method required. Maybe there was ordinary gas out there, too faint to see, filling in the missing weight. These were reasonable doubts, and for years they let the field set the problem aside. But part of the reason was simpler. The idea was too strange, and it rested on one man, one cluster, one measurement. Science does not overturn its picture of the universe on the strength of a single startling result, especially from someone as prickly as Zwicky. It waits for the finding to show up again, somewhere else, measured a different way by different hands. One measurement is a curiosity, a pattern is a fact. So the missing mass sat quietly in the literature for almost 40 years, a footnote most astronomers had heard of and few took to heart. It needed a second witness. It needed a place where the same impossible excess of gravity showed up so plainly and so repeatably that it could no longer be waved away as a quirk of one crowded cluster. That second witness came from an ordinary-seeming task, the patient tracing of how single galaxies spin, and the person who did the tracing night after night would turn Zwicky's curiosity into a problem the whole field could no longer ignore. To picture what Vera Rubin measured, start with something you already trust, the solar system. The planets circle the sun, and they do not all move at the same speed. Mercury, close in, races around at about 30 miles a second. Neptune, far out, crawls along at around 3. The pattern is clear and it makes sense. Nearly all the mass sits in the sun at the centre, so the farther a planet is from that pile of mass, the weaker the pull it feels, and the slower it needs to move to stay in its orbit. The outer planets lag. This is how gravity behaves around a central weight, and it had been understood since Newton. A galaxy looks, at a glance, like a bigger version of the same thing. A bright bulge of stars crowds the centre, and a thin disk spirals outward, thinning as it goes. Most of the light, and so you would think most of the mass, sits toward the middle, so the stars far out at the rim should behave like Neptune, They should drift slowly, having little mass out there to hold them and being far from the bright centre that holds most of it. In the 1970s, working with an instrument built by her colleague Kent Ford, Vera Rubin set out to measure exactly this. She studied the great spiral galaxy in Andromeda first, then dozens more. Her instrument could read the speed of the glowing gas at many points across a galaxy's disk, from the crowded centre all the way out to the faint edge. She expected to watch the speeds fall off toward the rim, the outer stars lagging like distant planets. They did not fall off. Rubin found that the stars and gas at the far edge of a galaxy were moving just as fast as those much closer in. The speed climbed as you went out from the centre, then flattened into a long level line that ran on and on to the very edge of the visible disk. The rim was not lagging. It was keeping pace, which meant something was pulling on it hard, something that did not thin out where the starlight thinned out. The stone on the string comes back here. If the outer stars are moving that fast and have not flown off into empty space, then the galaxy's grip on them must be far stronger than the visible matter allows, and crucially, that grip must keep growing as you move outward, adding mass in the dark long after the stars have petered out. The light ends, the mass does not. The cleanest way to say it is this. Each galaxy sits inside a vast, roughly round halo of unseen matter, far larger than the bright disk we photograph. The stars are a glowing coin dropped into the middle of a dark beach ball. The coin is what we see. The beach ball is what holds it all together. What made Rubin's work land where Zwicky's had not was its plainness and its sheer repetition. This was not one strange cluster, weighed by delicate assumptions. It was galaxy after galaxy, ordinary ones, spiral after spiral, all telling the same story with the same flat line. She measured them for years, and the pattern never broke. Wherever she looked, the visible matter was too light for the speed she saw. By the end of the 1970s, the missing mass could no longer be shrugged off as a quirk. It was everywhere, written into the turning of nearly every galaxy in the sky. But every measurement so far leaned on the same tool, the motion of glowing things, stars and gas. A doubter could still ask whether the trouble lay in the matter, or in our understanding of how gravity works over such distances. To answer that, astronomers needed a way to feel the dark mass that did not depend on watching anything move. There is a way to sense mass that has nothing to do with speed, or spin, or the motion of any star. It comes from Albert Einstein's picture of gravity, and it lets a heavy object announce its weight simply by bending the light that passes it. In Einstein's theory of general relativity, finished in 1915, gravity is not quite a force in the old sense. It is a bending of space and time around anything that has mass. A heavy object dents the space around it, the way a bowling ball dents a stretched trampoline, and everything nearby, including light, must follow the curve. Light always travels the straightest path it can, but when the space itself is curved, the straightest path bends. So a ray of starlight grazing a massive object gets deflected, nudged off its course by the dent in space. This was tested in 1919, when the astronomer Arthur Eddington watched a total solar eclipse and measured the positions of stars whose light skimmed past the darkened sun. The stars appeared slightly shifted from where they should have been, pushed aside by exactly the amount Einstein had predicted. The sun's mass had bent their light. The idea was no longer just elegant, it was real, and it was measured. Now scale that up. Put a whole cluster of galaxies between us and some far more distant galaxy behind it. The cluster's enormous mass bends the space around it, and the light from the background galaxy, on its long journey to us, curves as it passes through. The result is that the distant galaxy appears warped. Its image is smeared into arcs, stretched, sometimes split into several copies arranged around the cluster, like a face seen through the foot of a wine glass. This is called gravitational lensing, because the cluster acts as a giant clumsy lens made of gravity. Here is why that matters for the dark matter story. The amount of bending depends only on the total mass doing the bending. It does not care whether that mass glows. Light and dark, stars and the unseen stuff, all of it dents space in proportion to its weight. So an astronomer can look at how sharply a background galaxy's image is warped and work backward to the exact mass of the cluster in front, without ever measuring how anything moves and without assuming the cluster is calm and settled. When astronomers do this, they find the same answer that Zwicky and Rubin found, reached by a completely different road. The mass needed to bend the light is far greater than the mass that shines. Again and again, cluster after cluster, the lensing reveals far more matter than the glowing galaxies contain. And the lensing maps show where that hidden matter sits, spread through the cluster in a great invisible cloud, most of it not tracing the bright galaxies at all. This mattered enormously, because it broke the last easy escape. Every earlier clue, the racing galaxies of coma, the flat rotation curves, had leaned on the motion of luminous things and on our trust that gravity behaves the same way out there as it does here. Lensing leaned on none of that. It measured weight directly through the bending of light, an effect confirmed by a British eclipse expedition 60 years earlier and grounded in Einstein's tested theory. Two roads, motion and bending, arriving at the same excess of mass. That agreement is what turned a suspicion into a near certainty for most of the field. Still, both roads measured the total, the light and dark added together. What no one had yet done was catch a moment where the universe pulled the two apart, separating the visible matter from the invisible, and let us watch them lie in different places. That moment was waiting in a violent collision two clusters had suffered long ago. Far off in the southern sky, about 3.5 billion light-years away, two great clusters of galaxies once ran into each other. They did not stop. They passed through one another and kept going, and the wreckage of that pass is still spread across the sky. Astronomers call it the bullet cluster, and it may be the single clearest piece of evidence that dark matter is real and is something new. To read it, you have to know what a cluster of galaxies is actually made of, by weight. The galaxies themselves, although stars are a small part. The largest pool of ordinary matter is not in the galaxies at all. It is a vast, thin, superheated gas that fills the space between them, glowing in X-rays, holding most of the cluster's normal mass. And then, if the earlier clues are right, there is the dark matter, more than all the rest combined, unseen. Now watch what happens when two such clusters collide. The individual galaxies are mostly empty space between stars, so they sail past each other almost untouched, like two swarms of gnats passing through one another with barely a bump. The dark matter, if it interacts as weakly as we suspect, does the same. It flies straight through and comes out the far side, but the hot gas cannot. Gas meeting gas drags, piles up and slows, the way two splashes of water collide and stop while spray flies onward. So the collision should tear the cluster's parts apart. The galaxies and the dark matter should keep moving and pull ahead. The gas, most of the ordinary matter, should lag behind, stripped out and left in the middle. That is precisely what we see. X-ray telescopes reveal the hot gas sitting where the crash happened, in the centre, slowed and shocked by the impact. It even shows a blunt shock front shaped like a bullet, which gave the cluster its name. Meanwhile, the galaxies have swept on ahead, in two clumps, one on each side, out beyond the stranded gas. The decisive stroke came from gravitational lensing. Astronomers led by Douglas Clow mapped where the cluster's mass actually lay, by measuring how the whole collision bent the light of galaxies far behind it. If ordinary matter were the whole story, the mass would sit with the gas, in the middle, since the gas is where most of the ordinary matter is. It does not. The lensing map shows the mass sitting out on the two sides, with the galaxies, ahead of the gas, exactly where the dark matter should have coasted through and gone. So the weight and the glowing gas are in different places. The bulk of the mass has come uncoupled from the bulk of the ordinary matter and flown out ahead of it. There is no way to explain that by hidden gas or faint stars, because the gas is right there in the X-ray image, sitting in the centre, and the mass is plainly somewhere else. This is why the bullet cluster is so often shown as the clincher. Earlier evidence measured the total mass and found too much of it. Here the universe ran an experiment for us, smashing two clusters together and separating the visible matter from the invisible, letting us see them lie apart. The mass went one way, the light-giving gas went another. It also lands a blow on the main rival idea, that maybe there is no dark matter and gravity simply behaves differently on large scales. In a collision like this, a modified law of gravity should still keep the pull centered on where the ordinary matter is, on the gas. Instead, the pull is centered on emptiness, on the sides, where something unseen has carried the weight. The dark matter is not just a number in an equation, it has a location, and the deepest confirmation of all was written into light far older than any galaxy. Every clue so far has come from things that formed long after the universe began, galaxies and clusters that took billions of years to assemble. But there is a way to weigh the dark matter using light from the universe's infancy, light that has been travelling toward us for more than 13 billion years. Go back to the early cosmos, when everything was crammed into a small blazing hot space. For its first few 100,000 years, the universe was too hot for whole atoms to hold together. Electrons flew free, unattached to the nuclei, and free electrons are very good at scattering light. So the young universe was not clear. It was a glowing fog, opaque, like the bright interior of a cloud, with light unable to travel far before bouncing off another electron. Then the universe expanded and cooled, and at about 380,000 years old it crossed a threshold. It grew cool enough for electrons to settle onto nuclei and form the first stable atoms. The fog lifted. All at once, light could stream freely across space, and it has been streaming ever since. That first freed light still fills the sky today, stretched by the long expansion of the universe into faint microwaves. We call it the cosmic microwave background, and it is the oldest light there is, a photograph of the cosmos as it looked the moment it turned clear. The European satellite named Planck mapped this ancient light across the whole sky with exquisite care. The map is almost perfectly smooth, a uniform glow at about 2.7 degrees above absolute zero, the same in every direction. But not quite. There are tiny ripples in it, spots very slightly hotter and colder than the average, differing by only a few parts in 100,000. Those faint ripples are the fossil imprint of sound. In the hot early fog, ordinary matter and light were locked together, and they sloshed. Gravity tried to pull matter into clumps. The pressure of the light pushed back out, so the matter fell in and bounced out and fell in again, ringing like a struck bell, sending pressure waves rolling through the cosmic soup. When the fog lifted and the light broke free, it froze the pattern of those waves in place. The hot and cold spots we see are where the sound waves happen to be caught at that instant, some at maximum compression, some at full stretch. Here is the beautiful part. Dark matter took part in this ringing, but differently. It felt gravity, so it pulled matter inward, but it did not feel the pressure of light, because it does not interact with light. So it did not bounce, it only pulled. That difference changes the pattern. The exact sizes and heights of the ripples, how loud each note in the cosmic chord rings out, depend on how much ordinary matter was sloshing and how much dark matter was silently pulling. By measuring those ripples with precision, physicists can read off both amounts, the way you might tell the size and shape of a bell from the tone it makes. The answer that comes out of the oldest light agrees with all the rest. Ordinary matter makes about 5% of the universe's contents. Dark matter makes about 27%, more than 5 times as much. The remaining 68 or so % is a separate mystery called dark energy, a story for another night. So the count is settled from every direction. Spinning galaxies, bent starlight, colliding clusters, and now the faint hum of the newborn universe all give the same ratio of dark to bright. The evidence is overwhelming that something is there. which forces the harder question into the open. If it is not the ordinary matter we know, then what could it possibly be? The honest way to begin is by ruling things out. Faced with a great deal of missing mass, the first instinct of any careful scientist is not to invent something exotic. It is to reach for the familiar. Maybe the dark matter is just ordinary stuff that happens to be too faint to see. The universe is full of things that give off little or no light. Before anyone reaches for a brand new particle, they have to clear away the ordinary explanations one by one. Start with cold gas and dust. Space is full of it, and cold gas glows very weakly. Could there simply be far more of it than we thought, filling in the missing weight? The trouble is that gas and dust, even when cold, are not truly invisible. They absorb and re-emit light at wavelengths our telescopes can catch, and they block the light of stars behind them. When astronomers add up all the gas and dust they can detect across the sky, in radio waves and infrared, it falls enormously short, and crucially, it is made of ordinary matter, which the oldest light has already counted for us, capping how much can exist. Next, dead and dim stars. The galaxy is littered with faint, failed stars called brown dwarfs, too small to shine brightly, and with the burnt-out corpses of stars, the white dwarfs and neutron stars, and with lone black holes drifting through space. Lumped together, these were nicknamed machos, for massive compact halo objects. They are genuinely dark, or nearly so. Perhaps the halo around our galaxy is packed with them. This one could not be waved away by argument. It had to be tested, and it was, with a clever trick. When a dark, heavy object drifts in front of a distant star, its gravity bends the star's light and briefly brightens it. A small, telltale flare that swells and fades over days or weeks. This is gravitational lensing again, in miniature, and it works even for a lone dark object, because it needs no light of its own, only mass. Through the 1990s and after, dedicated surveys watched millions of stars night after night, counting these little flares to tally the dark, compact bodies in our galaxy's halo. They found some. They did not find nearly enough. The number of brightening events fell far below what would be needed if machos made up the missing mass. Dead stars and stray black holes are out there, but they are a minor part of the halo, not the bulk of it. Then there is the deepest limit of all, and it closes the door on every ordinary answer at once. All the candidates so far, gas, dust, dead stars, brown dwarfs, are made of the same basic building blocks as we are, protons and neutrons, the particles physicists group together as baryons, and the total amount of baryonic matter in the universe is not a free number we can inflate at will. It was fixed in the first few minutes after the Big Bang, when the lightest elements were forged, and it is stamped again into the ripples of the oldest light. Both measurements agree, and both say the same thing. There are simply not enough baryons in the entire universe to be the dark matter. Even if every proton and neutron were perfectly hidden, they would fall 5 times short. That is the wall the ordinary explanations run into. It is not that we failed to find enough faint gas or dark stars. It is that the total budget of normal matter, counted 2 independent ways, is far too small no matter how you hide it. The dark matter cannot be ordinary matter that forgot to shine, which leaves one door standing open, and it is a strange one. If the missing mass is not made of any particle we know, then it must be made of a particle we have never caught, something outside the entire catalogue of known matter. If dark matter is not gas, not dust, not dead stars, and cannot be made of protons and neutrons at all, then physicists are pushed to a remarkable conclusion. It must be a particle we have never discovered, one that lies outside everything in our best catalogue of matter. That catalogue has a name. It is called the Standard Model of Particle Physics, and it is one of the great achievements of the last century. It lists every kind of fundamental particle we have ever detected, and describes how they interact, and it has passed test after test with staggering precision. Every atom in your body is built from particles in that list. the quarks that make up protons and neutrons, the electrons that ring them, the photons that carry light, the neutrinos that stream through you by the trillions. It is a complete and beautifully tested inventory of the matter we know. And the strong hint from all the evidence is that dark matter is not on the list. To hold galaxies together, it has to have mass. To stay dark, it must not interact with light, which rules out anything electrically charged. To survive from the early universe until now, it must be stable, not decaying away over billions of years. And to explain how galaxies and clusters grew, it must be what physicists call cold, meaning its particles move slowly compared to light, so they can clump together under gravity rather than streaming out and smearing into a haze. The standard model does have one particle that comes close, the neutrino. Neutrinos have mass, they carry no electric charge, and they barely interact, slipping through matter like it is not there. For a while they seemed like a natural candidate, but they fail on one count. Neutrinos are feather-light, and were born moving at nearly the speed of light, which makes them hot, not cold. Hot dark matter would have streamed across the young universe and smoothed out the very clumps that later grew into galaxies. The universe we see, with its galaxies and clusters and great cosmic web, could not have formed from hot, fast-moving matter, so the one standard model particle that fit the other requirements fails the most important one. This is a genuine crossroads, and it is worth pausing on. The evidence for dark matter's existence is overwhelming and comes from many independent directions. Yet the best, most tested theory of matter we possess has no particle that can be it. Both of those statements are solidly established, and together they mean something profound. There is a kind of matter making up most of the universe, and it belongs to physics we have not yet written down. The standard model, for all its triumphs, is incomplete. That is not a disappointment to a physicist. It is an opening. It means there is new physics waiting out there, a particle or a whole family of particles beyond the known list, and dark matter is the loud, sky-filling clue pointing toward it. Whatever it is not rare. It outweighs everything we know 5-1. The universe is mostly made of something we have not yet named. So the task sharpens. We're no longer asking whether the mass is there. We're asking what new particle could carry it, one that is heavy enough to matter, dark enough to hide, stable enough to last, and slow enough to clump. Over the decades, one candidate rose above the rest, not because we had caught it, but because it seemed to fall out of the theories almost for free. It came with a name that has shaped the whole search, and a coincidence so neat that it looked, for a long while, like a signpost. Among all the guesses about what dark matter might be, one idea dominated the field for decades. The particle it describes has never been seen, but it earned its place at the front of the line by fitting the requirements almost too well. Physicists call it a WIMP, which stands for Weakly Interacting Massive Particle, and the plain meaning is right there in the name. Take the two words in turn. Massive means it has real heft, a substantial mass, likely somewhere between the weight of a single proton and a few thousand protons, though no one knows exactly. That heft is what lets a WIMP supply the gravity that holds galaxies together. Weakly interacting means it feels only two of nature's forces. It feels gravity, which is why we notice it at all, and it feels the weak nuclear force, one of the four fundamental forces, the same faint force that governs certain kinds of radioactive decay, so quiet and short-ranged that it lets particles slip past ordinary matter almost untouched. That second property is the key to why a WIMP would be dark. The weak force is aptly named. It reaches only across distances far smaller than an atom, and it acts so rarely that a particle feeling only the weak force and gravity could pass through solid matter, as if through open air. A WIMP could sail through the entire Earth, through all its rock and iron, and almost never bump into a single atom on the way. It does not touch the electromagnetic force at all, the force that carries light and binds atoms, so it neither gives off light nor blocks it. It would be genuinely invisible, felt only by its weight, and once in a great while, by the faintest possible nudge. Now think about what that combination gives you. A WIMP is heavy, so it clumps under gravity and moves slowly, making it exactly the cold matter that galaxies need to form. It is stable, at least in the simplest versions, so it lasts from the early universe to now without decaying. It does not shine, so it stays dark. Point by point, it matches the list of things dark matter has to be. On paper, it is a near-perfect fit. There was another reason WIMPs took hold, one that had nothing to do with dark matter at all. In the 1970s and 80s, physicists chasing deeper theories of particle physics, especially a framework called supersymmetry, kept finding that their equations predicted new heavy particles. These new particles were not invented to explain dark matter. They came out of attempts to solve unrelated puzzles in the Standard Model. Yet the lightest of them often turned out to be stable, heavy, and interacting only weakly. In other words, the theories built for other reasons kept producing, as a byproduct, exactly the kind of particle dark matter seemed to call for. Two separate roads, cosmology and particle theory, appeared to point at the same place. When an idea shows up unbidden from two directions, physicists take it seriously. Dark matter needed a cold, stable, weakly interacting massive particle. Theories of fundamental physics kept coughing one up on their own. It felt less like a lucky guess and more like a convergence, two great puzzles hinting at a single answer. But the strongest argument for WIMPs was still to come, and it was a piece of arithmetic so clean it earned a nickname. When physicists worked out how many of these particles the early universe would naturally leave behind, the number that fell out was not a rough match to the measured amount of dark matter. It was startlingly close, close enough to feel like a message. That coincidence became known as the WIMP miracle, and to see why it captivated a generation of physicists, we have to go back to the first hot moments of the cosmos. The most persuasive argument for the WIMP came not from watching the sky, but from running the clock of the universe backward to its first hot instance and asking a simple question. If these particles existed then, how many would be left over now? The answer that fell out was so close to the measured amount of dark matter that physicists gave it a name, the WIMP miracle. Go back to the universe when it was a fraction of a second old, unimaginably hot and dense, a furnace of particles slamming together. At that temperature, WIMPs would have been made and destroyed constantly. Two ordinary particles could collide and turn into a pair of WIMPs. Two WIMPs could meet and annihilate back into ordinary particles. Creation and destruction ran in perfect balance, and the universe held a steady, thick population of these heavy particles, as many being born each moment as were dying. Then the universe did what it always does. It expanded, and as it expanded, it cooled. Two things began to work against the WIMPs. First, as the temperature dropped, ordinary collisions no longer carried enough energy to make new WIMPs, so their creation slowed and then stopped. The WIMPs already present could still find each other and annihilate, but no fresh ones were being made. Their numbers should have plummeted towards zero. Second, and this is the crucial turn, the expansion of the universe was thinning everything out, spreading the particles farther and farther apart. To annihilate, two WIMPs must actually meet, and in a rapidly expanding space, meeting becomes harder and harder. At some point, the WIMPs simply got too spread out to find one another anymore. The annihilation effectively stopped, not because the particles were gone, but because they could no longer reach each other across the growing distances. Physicists call this moment freeze-out. The population of WIMPs, unable to be created and no longer able to destroy itself, froze at whatever number it happened to have reached. Those surviving particles would then coast, untouched, all the way down through billions of years to the present day. They are the leftovers, the relic abundance, the ones that never found a partner to annihilate with before the universe pulled everyone apart. Now here is the piece that stunned people. The final number of leftovers depends on one thing above all: how readily the WIMPs annihilate, which is set by the strength of their interaction. Interact too strongly, and they keep finding and destroying each other longer, leaving very few behind, interact too weakly, and they stop annihilating early, leaving a great many. So the leftover amount is tied directly to the interaction strength. When physicists plugged in the strength of the weak nuclear force, the very force a WIMP is supposed to feel, and calculated how many would be left after freeze-out, the answer came out almost exactly equal to the amount of dark matter we actually measure in the sky. Not within a factor of 1,000, not in the rough neighbourhood. Close, strikingly close, from a calculation that used only the weak force and the known expansion of the universe. That is the miracle in the name. A particle with roughly the mass and the weak force interaction that particle theories were already predicting, dropped into the early universe and left to freeze out, naturally produces about the right amount of dark matter on its own. Nothing was tuned to make it fit. The pieces simply lined up. For decades, that coincidence was the strongest reason to believe the dark matter was a WIMP, and it set the entire experimental program that followed. If the particle was really out there, the next task was obvious. We had to catch one, and there turned out to be 3 very different ways to try. If dark matter is a real particle drifting through space, then there are only 3 fundamentally different ways to get our hands on it, and physicists have pursued all 3 at once. You can wait for one to bump into you. You can watch for 2 of them destroying each other far away. Or you can try to make one yourself. Each strategy leans on a different one of the particle's expected habits, and each has its own kind of patience. The first way is called direct detection, and it is the most literal. If our galaxy is swimming in a sea of dark matter, then that sea is passing through you, and through the ground, and through everything, all the time. On very rare occasions, one of those particles should nudge the nucleus of an ordinary atom, giving it a tiny recoil, like an invisible marble clicking against a resting one. The whole game is to catch that faint click. Physicists build large, exquisitely sensitive detectors, often great tanks of liquid xenon, and bury them deep underground, beneath a mountain or in a mine. The rock overhead screens out the constant rain of other particles from space, so that in the deep quiet, the one in a very long while that could be dark matter might finally be noticed by the little flash and jolt it leaves behind. The second way is called indirect detection, and it turns the freeze-out story around. In the early universe, WIMPs annihilated when they met. That process never entirely stopped. In places where dark matter is packed densely today, at the crowded centre of our galaxy, or in the heart of the sun where it may collect, 2 dark matter particles should still occasionally find each other and annihilate, converting themselves into a spray of ordinary particles including light. So instead of building a detector on Earth, you point telescopes at those dense regions and look for the particular glow of dark matter, destroying itself, an excess of gamma rays or antimatter arriving from exactly where the dark matter should be thickest. You're not catching the particle, you're catching its death. The third way is the one this story follows, and it is the boldest. Instead of waiting for dark matter to come to you, or watching it annihilate far off, you make it from scratch. Einstein's most famous equation says that mass and energy are 2 forms of the same thing, and that energy can be turned into mass. Concentrate enough energy into a small enough space, and new particles condense out of it, particles that were not there before. If dark matter is heavy but not too heavy, then a machine that concentrates enough energy might manufacture it directly, conjuring a pair of dark matter particles out of pure collision energy, right here on Earth, where we can surround the event with instruments. 3 roads then: catch it passing through, catch it dying, or build it. They are wonderfully complementary, because each probes the particle in a different way, and a real discovery would ideally show up in more than one. A signal in a deep underground tank matched by a glow from the galactic centre, matched by particles made in a machine, would be the kind of triple confirmation that leaves no doubt. For decades, all 3 have been running, and all 3 have come up empty of a confirmed signal. But the third road has a particular power the others lack. If you make the particle yourself, in a place you control, then you also control the energy, the timing, and the instruments watching. You're not at the mercy of whatever the galaxy happens to send you. That control is the reason physicists built the most powerful machine of this kind ever attempted, and the reason our story now moves underground to a great ring straddling a border in Europe. There is a real advantage to making dark matter yourself rather than waiting for the universe to hand it over, and it is worth understanding before we step inside the machine built to try. The advantage comes down to a single word: control. Consider the other two approaches and what they cannot command. In direct detection, you build your deep tank and then you wait. You cannot choose when a dark matter particle will drift in and strike a nucleus, or how hard, or how often. You are a fisherman with a net in a dark river, entirely dependent on what the current carries past. If the particle interacts even more weakly than hoped, you might wait a lifetime and catch nothing, never knowing whether it was absent or simply too shy. In indirect detection, you point your telescope at the galactic centre and hope the dark matter there is dense enough and annihilates often enough to produce a glow you can pick out from the blaze of ordinary sources crowding the same patch of sky. Again, you take what the cosmos gives, at the distance and rate it chooses. A collider flips that relationship. In a collider, you decide when the collisions happen, and they happen on a schedule, many millions of times each second. You decide how much energy goes into each one, tuning the machine to concentrate exactly the energy you think is needed to make the particle you are hunting. And because the collision happens at a known spot at a known instant, you can build enormous layered instruments completely surrounding that spot, watching from every angle, catching almost everything that flies out. You're no longer a fisherman waiting on the river. You're running the river, choosing the moment and standing over the water with every kind of net at once. There is a second, subtler advantage. When you produce a particle in a collision, you also learn its mass and its properties from the debris in ways that the other methods struggle to pin down. A faint recoil in an underground tank tells you something touched a nucleus, but little about what. A collision that manufactures the particle, surrounded by detectors measuring the energy and direction of everything else that came out, can reveal the particle's weight and how it was made. You're not just confirming that dark matter exists, you are interrogating it. This is why, even with 3 roads open, the Collider Road carries a special hope. If dark matter is within reach of our energies, a collider could not only find it but characterize it, and could do so on demand, repeating the experiment as often as needed to be sure. The catch, of course, is the energy. To make a heavy particle, Einstein's equation demands you gather a tremendous amount of energy into a space smaller than an atom, and then do it over and over, because any single collision that makes dark matter would be extraordinarily rare. Gathering that much energy into that smaller space is one of the hardest engineering problems humanity has ever taken on. You cannot simply build a bigger battery. You have to take ordinary particles, protons plucked from hydrogen, and accelerate them to almost the speed of light, then steer 2 streams of them into a head-on crash so violent that the raw energy of the impact can freeze into new matter. The faster you drive the protons, the more energy each collision carries, and the heavier the particles you can hope to create. The machine built to do exactly this is a ring 17 miles around, buried beneath the countryside where Switzerland meets France. To understand how it turns Einstein's equation into a tool for hunting the invisible, we have to go inside it. Beneath the farmland and villages on the border between Switzerland and France, in a circular tunnel about 17 miles around and 100 meters underground, runs the largest and most powerful machine ever built. It is called the Large Hadron Collider, and it belongs to CERN, the European Laboratory for Particle Physics near Geneva. Its job is to take the smallest pieces of matter and smash them together as hard as physically possible. The ring is a racetrack for protons, the positively charged cores of hydrogen atoms. The machine strips electrons off hydrogen to get bare protons, then feeds them into the ring in 2 thin beams that travel in opposite directions, one running clockwise, the other counterclockwise. These beams are not loose clouds. Each is squeezed into narrow bunches, and each bunch holds many billions of protons packed tightly together, threading around the ring in lockstep. To push the protons to nearly the speed of light, the machine uses electric fields that give them a hard shove on every lap, adding a little more energy each time around. The protons circle the 17-mile ring more than 11,000 times every second, and with each pass they gain speed, until they are moving at more than 99.9% of the speed of light. At that velocity, a proton laps the entire ring in under 100 millionth of a second, and it carries an enormous amount of energy for so tiny a thing. Keeping those beams curving around the ring instead of flying straight out takes tremendous force, and that is the work of the magnets. More than 1,000 giant magnets bend and focus the beams, and they are not ordinary magnets. They are superconducting, made of coils that carry electricity with no resistance at all, which lets them generate fields far stronger than any normal magnet could. To become superconducting, the coils must be chilled to about 271 degrees below zero on the Celsius scale, colder than the deep space between the stars. The Large Hadron Collider is, among other things, one of the coldest places in the known universe, and it sits under a few Swiss and French villages. Then the two beams, each racing near light speed in opposite directions, are steered into one another at a few chosen points around the ring. When a proton from one beam meets a proton from the other head-on, the combined energy of the crash is concentrated into a spot far smaller than a single atom. The measure of that energy is written as 13 tera-electron-volts, a unit of energy used in particle physics. The number itself matters less than what it means. It is the most concentrated energy humanity has ever created in a controlled way, and by Einstein's rule that energy can turn into mass, that concentration is what makes new, heavy particles able to appear where none existed a moment before. Most of the time, the two protons simply glance off each other and little of interest happens. But every so often the collision is dead-on and violent, and in that instant the pure energy of the impact condenses into a shower of new particles that spray outward from the collision point. Some are familiar, some are heavy and unstable, existing for a flicker before decaying, and just possibly, in a very rare collision, some of that energy could freeze into a pair of dark matter particles, made on Earth for the first time. The trouble is that dark matter, if it is made, would fly out of the collision and vanish without touching anything, leaving no track and no glow. To catch a thing like that, you cannot simply look at the collision. You have to build a machine around it so complete, so all-seeing, that even an invisible particle betrays itself by the hole it leaves. Two such machines sit at points around the ring, and they are marvels in their own right. At two of the points where the beams cross, the tunnel opens into vast underground caverns, and inside each one sits a detector the size of a building, wrapped in layers around the exact spot where the protons collide. The two largest are called Atlas and CMS. Each was built by thousands of physicists from dozens of countries, and each has a single purpose: to take the chaos of a collision and turn it into a record precise enough to read. The design principle behind both is the same, and it is worth picturing. When protons collide, particles spray outward in every direction from the central point. So the detector is built as a series of nested shells, like the layers of an onion, each shell wrapped completely around the collision point, each one designed to measure a different property of the particles passing through. A particle born in the center must cross every layer on its way out, and at each layer it leaves a clue. Read all the clues together, and you can reconstruct what the particle was, where it went, and how much energy it carried. The innermost layer is the tracker. It sits closest to the collision and does something delicate. It records the paths of charged particles without stopping them, marking a series of points along each particle's flight so its track can be drawn. The whole tracker sits inside a powerful magnetic field, which bends the paths of charged particles as they fly. The amount of bending reveals each particle's momentum, its heft in motion. A fast, heavy particle barely curves. A slow, light one bends sharply, From the curl of the track, the detector reads the particle's momentum straight off. Outside the tracker come the calorimeters, and their job is to stop particles and measure their energy. Where the tracker lets particles pass through, the calorimeter is dense and thick, designed to absorb them completely. A particle plows in, dumps all its energy into the material as a shower of smaller particles, and comes to rest, and the detector measures the total energy deposited. There are two kinds, one tuned to catch electrons and photons, particles of light, and a heavier one further out to catch the sprays called jets, which come from the particles that make up protons. Almost everything is stopped by the calorimeters. There is one important exception, a particle called the muon, a heavier cousin of the electron. Muons punch straight through the calorimeters without stopping, so the very outermost layer of the whole detector, the largest shell of all, is built to catch them. That is why muon chambers form the outer skin of ATLAS and CMS, the last net, sized to spot the one ordinary particle tough enough to get that far. So a particle's journey through the detector reveals its identity by where and how it is caught. Left a track and stopped in the light-catching calorimeter, it was an electron or a photon. Left a track and stopped in the heavy calorimeter, it was part of a jet. Passed through everything, and only registered in the outer chambers, it was a muon. Left a track that curved but never deposited its energy anywhere, it was some other charged particle. Every known particle has a signature, a particular pattern of clues across the layers. This is the machine's great strength and, for dark matter, its central problem. The detectors are built to catch things. They are a nearly closed sphere of sensors, designed so that any ordinary particle flying out of a collision will strike some layer and be recorded. But dark matter, by its nature, would strike nothing. It would pass through the tracker, through both calorimeters, through the muon chambers, through the entire building-sized instrument, and out the far side without leaving a single mark. It would be the one thing in the collision that the great all-seeing machine cannot see. Catching the invisible then requires a trick, and it turns out the trick was there all along, hidden in a law as old as physics itself. Here is the beautiful idea at the centre of this whole search. You cannot detect a particle that touches nothing, but you can notice that it left by carefully adding up everything else and finding that some momentum has gone missing. The invisible particle betrays itself not by what it does, but by the gap it leaves in the books. The principle behind this is conservation of momentum, one of the oldest and most reliable laws in physics. Momentum is a measure of motion, how much a thing is moving and in what direction, and the law says it can never simply vanish. In any collision, the total momentum afterward must equal the total momentum before. If two things crash and pieces fly off, all those pieces, added up as arrows pointing in their directions of travel, must balance out to the same total the system started with. Nothing is created from nothing, and no motion disappears. Now apply that to the collider, with one clever adjustment. The two proton beams race directly toward each other, head-on, along the line of the tunnel. Physicists focus on the momentum in the directions crosswise to that line, the sideways momentum out in the plane perpendicular to the beams. Before the collision, the protons are moving almost purely along the beamline, so their sideways momentum is essentially zero. There is no net motion to the left or the right, up or down. The books start balanced at zero in every crosswise direction. That means that after the collision, when the debris sprays outward, the sideways momentum of everything that flies out must also add up to zero. Draw an arrow for every particle that comes out, sized by its momentum and pointed in its direction, and the crosswise components of all those arrows must cancel, pulling equally in all directions around the beamline. If one particle flies out hard to the left, something must balance it, flying to the right. The total, added up all the way around, has to come back to nothing. So imagine a collision where the detector catches a spray of particles, measures every one, adds up all their sideways arrows, and finds that they do not cancel. They add up to a strong push in one direction, say off to the left with nothing on the right to balance it. The books do not close. Momentum that should be there is simply gone. By the ironclad law of conservation, that missing momentum cannot have vanished. It must have been carried off by something the detector did not see, something that flew out to the right, invisibly, balancing the books in a ledger the instruments could not read. Physicists call this missing momentum, and it is the single fingerprint an escaping particle leaves behind. The detector never sees the dark matter. It sees the imbalance the dark matter caused, an unbalanced spray of ordinary particles leaning one way, revealing that something unseen must have flown the other. It is like watching a cannon fire on a still lake and seeing the boat lurch backward, even though the cannonball itself has already sailed off into the fog. You did not see the ball. You saw the recoil, and from the recoil you know the ball was there. This is the whole strategy for catching dark matter in a collider. You do not look for the particle. You look for the hole it leaves, the missing momentum in an otherwise balanced event. Any collision that produces an invisible particle should show this telltale imbalance, this recoil against nothing. But there is a difficulty hiding in that plan. To notice that momentum is missing, you need something visible for it to recoil against, some ordinary particle flying off in the opposite direction to mark the imbalance. A collision that made only dark matter and nothing else would produce no visible spray at all, nothing to see and nothing to measure. So the searches lean on a particular kind of event, one where the dark matter is thrown out alongside a single visible companion. To see missing momentum, you need something visible in the frame to measure it against. A collision that produced only dark matter would leave the detector completely empty, and an empty detector looks exactly like a collision, where nothing interesting happened at all. There would be no way to tell a batch of invisible particles from a near miss, so physicists hunt for a particular, telling arrangement where the dark matter is made together with one ordinary particle that recoils against it. The idea rests on how these collisions actually unfold. When two protons crash, the pieces inside them can radiate, throwing off an ordinary particle just before or during the main event, the way a swerving car might fling a spray of gravel. So a collision that makes a pair of dark matter particles might also, in the same instant, spit out one visible particle off to the side. Now the event is no longer invisible. You have one ordinary particle flying out one way, and a pair of dark matter particles flying out the other, unseen. The visible particle is the marker. The dark matter is the missing momentum balancing it. This is called a mono-X search, where the X stands for whichever single visible particle came along for the ride. The two most important versions are the monojet and the monophoton. In a monojet event, the visible companion is a jet, a tight spray of ordinary particles that appears when one of the quarks or gluons inside the proton is knocked loose and flung outward. In a monophoton event, the companion is a single photon, one particle of light thrown off from the collision. Either way, the picture is the same and strikingly clean. One thing flies out visibly in one direction, and on the opposite side there is nothing, no track, no energy, no spray, just a great gap in the momentum where something unseen must have gone. Picture what that looks like inside the detector. Almost the entire instrument is quiet. Then, on one side, a single jet or a single photon blazes out, carrying a healthy dose of momentum in its direction. And the detector, adding up every scrap of sideways momentum, finds that this lone jet or photon is not balanced by anything. There is nothing on the far side to cancel it. The event is lopsided, a single visible particle recoiling hard against pure emptiness. That lopsided picture, one thing against nothing, is the signature the searchers are built to find. It is as close as we can come to a photograph of dark matter being made. The reason this signature is so prized is that it is simple and generic. It does not depend on the fine details of what dark matter is. Whatever the particle turns out to be, if it is produced in a collision and then escapes without interacting, it will carry off momentum and leave this same imbalance. So the mono-X search is a wide net, sensitive to many different theories of dark matter at once, asking only the most basic question. Was something invisible made here, and did it fly away? The difficulty is that a lopsided event, one jet against nothing, is not unique to dark matter. The standard model itself produces events that look almost identical. There is a particle called the neutrino, a known, nearly invisible particle that also sails out of the detector unseen and also carries off missing momentum. Certain ordinary collisions throw off a jet alongside a pair of neutrinos, and to the detector that looks very much like a jet alongside a pair of dark matter particles. The visible jet is there. The momentum is missing. The picture matches. So the search is not simply a matter of spotting lopsided events. It is a matter of counting them extremely carefully and comparing that count to how many the ordinary, known processes should produce all on their own. And that counting problem grows immense because of just how many collisions this machine is throwing every single second. Inside the Large Hadron Collider, the two proton beams do not cross just once in a while. Where they meet, at the heart of Atlas and at the heart of CMS, the bunches of protons pass through each other about 40 million times every second. Each of those crossings is not a single collision, but a small storm of them, with dozens of proton pairs smashing together in the same instant, layered on top of one another at the very same point. Try to hold the scale of that in your mind. 40 million crossings a second, each one a burst of collisions, every burst spraying out hundreds of particles that fan through the layers of the detector. The machine is producing something like 1 billion actual proton collisions every second, hour after hour, day after day, whenever the beams are running. It is the most crowded, fastest stream of events humanity has ever generated in one place. That flood is the whole point. Remember why the collisions have to be so many. If dark matter can be made at all, it will be made only in the rarest of crashes, perhaps once in many billions or trillions. To have any hope of catching a handful of those rare events, you must run an enormous number of ordinary ones, the way you would need to pan through tons of river gravel to find a few flecks of gold. The rarity of the prize forces the sheer volume of the search. You cannot make the signal more common, so you make the collisions more numerous, and you sift. But the flood creates a problem as hard as any in the whole enterprise, and it is a problem of plumbing as much as physics. Each interesting collision, fully recorded with every track and every energy deposit across the whole detector, is a large chunk of data, on the order of 1 million bytes. Multiply that by 40 million crossings a second, and the number becomes absurd. The detectors would generate something like tens of trillions of bytes every single second. No storage system on Earth, not the largest data center ever built, could write down that torrent and keep it. If you tried to save every collision, you would fill any conceivable archive in moments, and then have nowhere left to put the next second of running. So a hard truth sits at the center of the experiment. The machine produces vastly more collisions than anyone can possibly record. The overwhelming majority of them, more than 99.9%, can never be saved. They happen, they spray through the detector, and then they are gone forever, unrecorded, unremembered, washed away to make room for the next flood coming a fraction of a second behind. Only a tiny, carefully chosen fraction can be written to disk and kept for study. This forces a decision of startling weight, and it must be made in almost no time at all. Out of 40 million crossings a second, only a few hundred to a few thousand can be permanently recorded. Every other one has to be thrown away, and that choice, which collisions to keep and which to discard, cannot wait for a human being to look. There is no time. It has to be made automatically in a sliver of a second by a system deciding on the fly which collisions look interesting enough to be worth their place in the archive, and which are ordinary enough to let vanish. That system is the gatekeeper of the entire experiment. Everything physicists will ever know about these collisions passes through it first. Whatever it keeps, they can study for decades. Whatever it drops is lost the instant it is dropped, with no way to get it back. And here is where the story sharpens toward its strange conclusion. because a system built to recognize interesting collisions can only recognize the kinds of interesting it was told to look for. To understand how dark matter might slip through, we have to meet the gatekeeper itself. The system that decides, in a fraction of a second, which collisions to keep is called the trigger. It is not a single device but a layered chain of them, part fast electronics and part banks of computers, and its task is brutally simple to state and fearsomely hard to do. Look at each collision as it happens, decide almost instantly whether it is worth saving, and if not, let it go. The trigger works in stages because there is not enough time to think hard about every collision. The first stage is built directly into custom electronics, wired close to the detector, and it is crude and lightning fast. It does not reconstruct the whole event. It glances at a few simple things, whether there was a big deposit of energy in the calorimeter, or a high momentum muon punching out to the muon chambers, or a large amount of missing momentum leaning to one side. Based on those quick signs, it makes a snap judgment, and it makes it in a few millionths of a second. Most collisions fail this first glance and are dropped at once, cutting the torrent from 40 million a second down to about 100,000. Those survivors pass to the next stage, a large farm of computers that can afford a little more time, a few hundredths of a second each, to look more carefully. This stage does something closer to reconstructing the event, piecing together tracks and energies well enough to ask sharper questions. Does this collision really have the features we care about? Is the missing momentum genuine or an artifact? Out of the 100,000 that reach this stage, only a few hundred to a few thousand survive it. Those, at last, are written to permanent storage. Everything else is gone. The trigger, then, is a filter of ferocious severity. It throws away more than 99.9% of all collisions, and it does so on the basis of rules written in advance by physicists. Those rules are called trigger menus, and they are essentially a list of the kinds of events worth keeping. An event with a very energetic jet, keep it. An event with 2 high-energy muons, keep it. An event with large missing momentum above some threshold, keep it. Each rule is a description of something interesting, and only collisions that match one of the descriptions earn a place in the record. There is deep wisdom in the design, and also a deep limitation, and the two cannot be separated. The wisdom is that the trigger lets the experiment run at all. Without it, there would be no way to cope with the flood, and no physics could be done. The limitation is that the trigger can only keep what its rules were written to recognize. It is a gatekeeper with a fixed list of names, admitting the guests it was told to expect and turning away everyone else, and it turns them away for good. Now think about what that means for a search for something genuinely new. The rules were written by people, based on the theories they had in mind, tuned to catch the signatures they expected dark matter or other new particles to produce. A monojet with large missing momentum, yes, there is a trigger for that. But dark matter might not announce itself that way. If the real particle produces a signature no one thought to write a rule for, one that does not trip any threshold on the menu, then the trigger will treat it as ordinary and let it vanish, 40 million times a second, night and day. The collision that finally holds the answer might happen and be seen by the detector and be discarded 100,000th of a second later because nothing in the menu was written to notice it. To feel the full weight of that, we have to look closely at what it means for a real signal to be thrown away. Sit with the hardest possibility in this whole story. The collision that makes dark matter for the first time may already have happened inside Atlas or CMS and been thrown away before any person could ever look at it. Not lost in analysis, not buried in noise, discarded at the gate in a fraction of a second by a trigger whose rules did not have a place for it. To see how that could happen, remember what the trigger is built to catch. Its rules were written by physicists working from the theories they trusted, and for dark matter, the leading theory was the WIMP, producing that clean signature of a single hard jet or photon recoiling against large missing momentum. So the triggers were tuned for exactly that. a big visible object and a big imbalance. If the real dark matter produces that picture, the trigger will catch it, and the search will work as designed. But nature was under no obligation to make dark matter look the way we guessed. Suppose the particle is on the lighter side so that when it is made, the visible jet recoiling against it is soft, carrying only modest momentum, below the high threshold the trigger demands. The event is real. Dark matter flew out of it. But the visible marker is too gentle to trip the rule, so the trigger sees an unremarkable low-energy collision, one of billions, and drops it. The signal was there. The gatekeeper was looking for something louder. Or suppose the dark matter does not escape immediately at all, but is produced through some intermediate particle that decays in an unusual way, leaving a pattern of tracks and energy that matches none of the expected signatures. The trigger scans for the shapes it knows, the big jet, the pair of muons, the clean missing momentum. It does not find any of them, because this event has a shape no one wrote a rule for. So it is judged ordinary and let go, even though it carried something no experiment has ever confirmed. This is the quiet tragedy hidden inside the machine's greatest strength. The very filter that makes the experiment possible also enforces the assumptions of whoever wrote it. The trigger cannot keep what it was not told to value. It is exquisitely good at catching the kinds of new physics we imagined in advance, and completely blind to the kinds we did not. A genuinely surprising signal, one that does not resemble our theories, is precisely the kind most likely to be thrown away, because surprise is what the rules were not built to expect, and once an event is dropped by the trigger, it is gone in the fullest sense. There is no backup, no lower quality copy kept just in case. The detector saw it, the electronics judged it, and the electronics let it fall, and the next collision took its place a fraction of a second later. You cannot go back and rerun that exact crash. Each collision is a unique event in time, and the ones the trigger discards are erased from history at the moment of discarding. So when physicists say dark matter might already be buried in old data, they mean something layered and a little haunting. Part of what they mean is hopeful, that the collisions we did keep, the ones the trigger saved, might hold a signal we have not yet recognized in them. But part of it is a warning that some of the answer may have been in the collisions we did not keep, thrown away by a gatekeeper following rules that never imagined it. That double meaning drives everything that follows because it changes the question. The task is no longer only to build better machines. It is to think harder about what we might have failed to look for, starting with the particle that would connect our world to the dark one. If dark matter is ever going to be made in a collider, or ever going to strike a detector underground, there has to be some bridge between our kind of matter and the dark kind. The two must be able to talk to each other, at least faintly, or dark matter could never be produced from ordinary collisions and could never leave a trace anywhere. Physicists call that bridge a mediator, and it may be the most important missing piece in the whole search. Think about why a bridge is needed at all. Dark matter, by definition, barely interacts with ordinary matter, but barely is not never. For the WIMP miracle to work, for dark matter to have annihilated in the early universe and frozen out at the right amount, there had to be some force, some channel, through which dark matter and ordinary matter could turn into each other. And for a collider to make dark matter from a proton collision, that same channel has to run in reverse, letting the energy of ordinary particles convert into dark ones. Something has to carry the interaction across the gap between the two worlds. In the standard model, every force is carried by a particle. The electromagnetic force is carried by the photon. The strong force that binds quarks is carried by gluons. The weak force is carried by heavy particles called the W and the Z. In each case, when two particles interact, they do it by exchanging a carrier, tossing an invisible messenger back and forth that transmits the force between them. A mediator for dark matter would be one more such carrier, a new particle whose whole job is to pass the interaction between ordinary matter and dark matter. Picture two people standing on separate islands, unable to reach each other directly. If they are to trade at all, there must be a boat running between the islands, carrying goods back and forth. The mediator is that boat. Without it, the two islands are sealed off and no exchange is possible. With it, however rarely the boat makes the crossing, trade can happen. The mediator is what makes dark matter reachable from our side at all. What might this mediator be? It could be a heavy new particle, something like a heavier cousin of the Zed, sometimes called a Zed prime, a carrier that couples to both ordinary quarks and dark matter. It could be tied to the Higgs particle, the one the Large Hadron Collider famously discovered in 2012, letting the Higgs act as a doorway to the dark sector. It could be something stranger still. No one knows, because the mediator, like the dark matter itself, has never been seen. And here is the turn that matters for the search. If a mediator exists, then a collider might make the mediator directly, even more easily than it makes dark matter. The mediator, being a bridge to ordinary matter, would by its nature couple to the quarks inside protons, which means proton collisions could produce it. Once made, that mediator could decay in two different ways. Sometimes it would decay into a pair of dark matter particles, invisible, giving the missing momentum signature. But sometimes it would decay back into ordinary particles, a pair of quarks that appear as two jets, fully visible in the detector. That second possibility opens a completely different way to hunt. Instead of looking for the invisible dark matter, you look for the visible decay of its bridge, searching for the mediator itself appearing as a bump in the data at some particular mass. The mediator might be easier to catch than the dark matter it connects to. But to search for something whose exact nature you do not know, you need a way to describe it honestly, without pretending to a certainty you lack. And that need gave rise to a particular modest style of theory. When physicists first hunted for dark matter at the collider, many of them used grand, complete theories, especially supersymmetry, the elegant framework that predicted a whole zoo of new particles at once. These theories were beautiful and detailed, but they carried a hidden cost. They came with dozens of unknown numbers, dozens of free choices, and a search built around one specific version of the theory could easily miss dark matter if nature had chosen a slightly different version. You could rule out one elaborate model and learn very little about the others. So over time, the field shifted toward a humbler and more honest approach, called simplified models. The idea is to strip away everything you do not need and keep only the few pieces the search actually depends on. For a dark matter search, that means just 3 ingredients: a dark matter particle with some mass, a mediator, the bridge, with its own mass, and the strength of the coupling, how firmly the mediator ties the two worlds together. That is nearly all. You do not commit to a full theory of everything. You describe only the minimal cast of characters the collision needs. The power of this modesty is that it makes the search clear and general. With only a few knobs to turn, physicists can lay out their results as a simple map. Along one direction, the mass of the dark matter particle. Along another, the mass of the mediator. Every point on that map is a specific possibility, a particular pairing of masses, and the experiment can ask for each point whether the collisions rule it out or leave it standing. The result is a chart of what has been excluded and what remains open, readable at a glance, not tied to any one grand theory. Think of it like mapping an unknown coastline. You could try to draw the whole continent at once, every river and mountain, and risk getting most of it wrong. Or you could sail the edge carefully and mark just 2 things, how far north you are and how far west, filling in a grid of where you have been and where you have not. The simplified model is that grid. It does not pretend to know the interior. It records, honestly, which stretches of the possible have been explored and found empty, and which have not yet been reached. This honesty matters enormously for the question of buried data, and here is why. Because a simplified model has so few assumptions, its results can be reused. A search designed around one simplified model can often be reinterpreted, its data asked about a different dark matter mass, a different mediator, without rerunning the machine. The stripped-down description acts like a common language. Results spoken in that language can be translated and reapplied as new ideas come along, which means an old search can keep giving answers to questions it was not originally built to ask. There is a limit to the modesty, and good physicists say it plainly. A simplified model is not the truth. It is a deliberate cartoon, a stand-in that captures the collider-relevant physics while ignoring everything else the real theory might contain. If nature is more complicated, and it may well be, the simplified model could miss features that matter. It is a tool for organizing the search, not a claim about what dark matter really is. Its virtue is that it is transparent about exactly what it assumes, so that everyone can see the edges of what has been tested. Even with this flexible, honest framework, the searchers so far have assumed one thing, almost without question, that dark matter, once made, leaves the detector immediately, escaping in the same instant it is born. That assumption is baked into the missing momentum strategy, but nature may not honour it. Some forms of dark matter might not leave right away. They might linger. Almost every dark matter search at the collider rests on one quiet assumption, that the dark matter particle, the moment it is created, flies straight out of the detector and escapes. That is why the whole strategy is built on missing momentum. The particle is assumed to be gone before it can interact, leaving only the hole it made. But there is no law that forces dark matter to behave so promptly. It might instead be produced through particles that linger, travelling a measurable distance before they decay, and that possibility opens a whole territory the standard searches were never built to explore. To see how this works, think about the range of lifetimes particles can have. Some unstable particles decay almost the instant they are born, in a tiny fraction of a second, so close to the collision point that they seem to vanish on the spot. Others live far longer. The muon, for example, lives a comparatively lazy couple of millionths of a second, long enough that it sails clear out of the detector before decaying. Between those extremes lies every intermediate possibility, particles that live just long enough to travel a short but real distance before falling apart. Now imagine a new heavy particle, perhaps the mediator or some partner particle in the dark sector, that is produced in a collision and then lives for a little while before decaying into ordinary matter or into dark matter. If its lifetime is in a certain range, it will not decay at the collision point. It will fly outward first, crossing a few millimeters or a few centimeters or even several meters through the detector, and only then break apart, releasing its decay products somewhere out in the layers, far from where the protons actually collided. Physicists call these long-lived particles, and they are one of the most interesting frontiers in the whole hunt. The reason is subtle and important. All the ordinary machinery of the detector, the tracking, the reconstruction, the trigger rules, was built around a basic expectation that interesting particles are made at the collision point and their decay products come streaming out from that single central spot. Every track is fit, assuming it begins at the center. Every event is read as a spray from one origin. That assumption is correct for almost all known physics, and it works beautifully. But it is exactly wrong for a long-lived particle, which decays not at the center, but somewhere out in the volume, off to the side, well away from where everything is supposed to begin. Picture a fireworks show where you have learned to expect every burst to bloom from a single launch point low on the horizon. You point your camera there, you time your shots to that spot, and you catch every shell. Then one shell drifts far off to the side before it bursts, blooming in a corner of the sky your camera was never aimed at. The burst is real, bright, unmistakable, and yet your whole setup was arranged to miss it, because it did not come from where bursts are supposed to come from. That is the situation with long-lived dark matter particles. If they exist, they would produce signatures that the standard searches, and even the standard triggers, are poorly built to notice. Decays happening in the wrong place, tracks appearing out of nowhere, energy deposited far from the centre with no track leading up to it. An experiment tuned to expect everything from the collision point can look right past a decay that happens a foot away. And this is where the buried data idea becomes concrete and almost tangible. If long-lived particles were produced in past collisions, their strange off-center signatures may sit in the recorded data right now, unrecognized, because no one was looking for a decay in that unexpected place. The clue would be a very particular kind of track, one that begins not at the heart of the collision, but somewhere it has no business beginning. When two protons collide inside the detector, essentially everything is supposed to come from one point, the exact spot where the beams crossed and the collision happened. Physicists call that spot the primary vertex, the vertex being the point where tracks meet and begin. Draw the paths of all the particles flying outward and trace them backward, and they should all converge on that one central origin, like spokes meeting at the hub of a wheel. That convergence is so reliable that the whole reconstruction of an event is built around it. But a long-lived particle breaks the pattern in a specific, detectable way. Suppose such a particle is made at the primary vertex and then flies outward before decaying. When it finally decays, say a few centimeters out, its decay products, the ordinary particles it breaks into, appear to spring from that off-center point, not from the collision center. Trace their tracks backward, and they do not meet at the hub. They meet at a second point displaced from the center, out in the body of the detector. This is called a displaced vertex, a place where new tracks begin that is offset from where the collision actually happened. A displaced vertex is a startling thing to see, because it looks, at first, almost impossible. Here are tracks, clearly real particles moving through the detector, and yet they do not come from the collision point. They seem to materialize out of empty space a few centimeters off to the side, with nothing connecting them back to the center, as if particles had appeared from nowhere in the middle of the instrument. There is only one sensible explanation. Something invisible travelled out from the collision, carrying no charge and leaving no track of its own, and then decayed at that spot, giving birth to the visible tracks that seem to start there. That signature is spectacularly clean in principle. Ordinary collisions almost never produce tracks that begin far from the center. The standard model has a few processes that can mimic it faintly, but a clear displaced vertex, tracks springing from empty space well away from the collision point, is close to a smoking gun for new physics, for exactly the kind of long-lived particle that could belong to the dark sector. If you could reliably find displaced vertices, you would have a powerful and low background way to hunt for dark matter's hidden relatives. The catch, the reason this is a frontier and not a solved problem, is that the detectors and their software were not originally built to look for them. Standard reconstruction assumes tracks begin at the center. Some early algorithms would actively discard a track that did not point back to the primary vertex, treating it as an error, a glitch, a mistake in the measurement, rather than a genuine particle from a displaced decay. The very thing that marks a long-lived particle, a track that does not come from the center, was the thing the software was told to distrust. The signal looked like noise, and noise gets cleaned away. So it is entirely possible that displaced vertices, real ones, from real long-lived particles, are sitting in data already recorded, either unnoticed because no one searched for them, or actively removed because the reconstruction threw out the strange tracks that made them. This is the buried data idea in its sharpest form. The evidence might not be missing because the collision never happened. It might be missing because the tools were built to look only at the center, and the answer was waiting a few centimeters to the side. Recognizing this, physicists have gone back and written new, dedicated searches for displaced vertices, carefully re-examining data with tools built to trust the off-center tracks rather than discard them. But there is a deeper bottleneck upstream of all of this, at the trigger, where so much is thrown away in the first place, and solving that led to a clever change in how the data itself is recorded. The tightest bottleneck in the whole search is the trigger, and the reason is simple bookkeeping. Every collision the experiment keeps has to be written to storage, and a full recording of one collision, with every track and every energy deposit across the entire detector, is large. Because each saved event is so heavy, only a few hundred to a few thousand can be kept each second. The size of each recording sets a hard ceiling on how many collisions survive. Save fat events, and you can save only a few. Physicists found a clever way around this, and it rests on a trade. What if, for certain kinds of searches, you did not need the full, detailed recording of each collision? What if a stripped-down summary would do, holding just the handful of quantities the search actually cares about, and throwing away the rest? A summary is far smaller than a full event, and if each saved event is much smaller, then for the same total storage, you can save far more of them. You trade depth for breadth, keeping less about each collision so you can keep many more collisions overall. This technique is called data scouting, or sometimes trigger-level analysis, and the idea is elegant. For a collision, instead of recording the complete detector readout, you record only a compact summary, perhaps just the jets and their energies and directions, computed quickly right at the trigger level. That summary might be a small fraction of the size of the full event. Because it is so light, the trigger can afford to keep collisions it would otherwise have had to throw away, admitting events with lower energy jets, softer signatures, the very kinds that the standard high-threshold triggers discard for lack of room. Here is why this matters so directly for dark matter. Remember the danger from before, that dark matter might produce a signature too soft to trip the ordinary triggers, a jet or a decay below the high thresholds the menus demand. Those thresholds are set high, in part because storage is scarce, and you cannot afford to keep the flood of low-energy events. Data scouting loosens exactly that constraint. By recording only a summary, the experiment can lower its thresholds and keep the softer collisions, the ones that might hold light dark matter or a low-mass mediator, without drowning in data. It widens the gate precisely where the standard search was blind. The cost of the trade is real and worth stating plainly. A scouted event is a summary, not the whole picture. You have the jets, but you may have thrown away finer details you might later wish you had kept. If something surprising turns up in scouted data, you cannot always go back and examine the full collision, because the full collision was never saved. You chose breadth over depth, and depth is what you gave up. So data scouting is powerful for searches where you know in advance which few quantities matter, and less useful when the surprise lies in the details you discarded. Still, the payoff has been striking. Using data scouting, physicists have searched for low-mass mediators, those bridge particles decaying into pairs of jets, in regions of mass that the ordinary triggers could never have reached, because the events were too soft and too numerous to save in full. They have set new limits on dark matter's bridge in exactly the corners the standard searches left dark. It is a direct answer to the buried data worry, a way of keeping collisions that would otherwise have been thrown away at the gate. Data scouting keeps more of the data inside the collaboration. But there is another, more radical way the buried signal might be reached, one that does not depend on being a member of Atlas or CMS at all. It depends on the data being open to the entire world. For most of the history of particle physics, the data from a great experiment stayed inside the collaboration that produced it. Thousands of physicists at Atlas or CMS had access, but no one else. The recording sat on servers at CERN, studied by the members, closed to everyone outside. There was nothing sinister in this. The data is fiendishly complex, hard to interpret without deep knowledge of the detector, and the collaborations had every reason to work through it themselves. But it meant that if the members did not think to ask a particular question, that question went unasked, and any answer hidden in the data went unfound. In recent years, that has begun to change, through something called open data. The Large Hadron Collider experiments, CMS in particular, have started releasing portions of their collision data to the public, placing it in an archive that anyone in the world can download and study. Not a summary, not a press release, but the actual recorded collisions, in a form researchers outside the collaboration can reopen and analyse. Years of collisions, hundreds of millions of real events, made freely available through the CERN Open Data Portal for anyone with the skill and the patience to look. The significance of this is easy to miss and genuinely large. It means the pool of people who can search the data is no longer limited to the few thousand members of the big collaborations. A physicist at a small university with no formal tie to CERN, a theorist with a new idea, a graduate student anywhere on Earth, can pull down real collisions and hunt through them for signatures no one inside thought to seek. The searching is no longer bottlenecked by the imagination of one collaboration. It is open to the imagination of the whole field, and this connects directly to the buried data idea. If dark matter's fingerprint is sitting in already recorded collisions, unrecognized because no one framed the right question, then the more eyes and the more ideas brought to that data, the better the chance someone finally asks the question that reveals it. Open data turns the archive from a private holding into a public commons, where a signal missed by the original searchers might be caught by an outsider, looking from an angle no one inside had tried. There have already been real results from open data, and not only from within CERN. Independent researchers have used public collision data to perform new analyses, rediscovering known particles as proof the method works, and carrying out genuinely novel studies that the collaborations had not done. Teams outside the experiments have developed new techniques on open data and found effects in it that the original members had passed over. The data proved to hold more than its first readers had drawn from it, which is exactly the point. There are honest limits. Open data is a subset, not everything, and it comes with the same deep difficulty that always attends this work, that understanding a collision truly requires understanding the detector that recorded it, its quirks and blind spots and calibrations. An outsider can reach wrong conclusions by missing some subtlety the insiders know. So open data is not a magic key. It is an invitation, an enormous archive laid open with the honest acknowledgement that no single group can think of every question worth asking of it. Open data lets new people search old collisions, but there is a related move, one that does not even require new people, only new questions put to old, finished results. It is a way of asking an experiment that has already published its answer to quietly answer something else as well. Every search at the Large Hadron Collider ends in a published result, and for a long time that result was treated as a closing door. A group would design a search for some specific particle, run it, find nothing, publish a limit saying that particle does not exist in such and such a range, and move on. The analysis was finished, the paper was written, the door was shut. But physicists came to realize that a finished search need not be finished at all. The same data, the same result, could often be asked an entirely different question, one the original authors never had in mind. This reuse is called recasting. The idea works because of how these searches are actually built. A search for new physics is essentially a filter. It selects collisions with certain features, a hard jet and large missing momentum, say, then counts how many passed and compares that to how many the standard model alone should produce. If the counts match, no new physics is seen, and a limit is set. But that filter, that selection and count, does not care what theory motivated it. It simply counts events with certain features, and a different theory, a different dark matter model the authors never considered, might also produce events with those very same features. So recasting means taking a published search, with its exact selection and its exact counts, and asking whether some new model, invented or refined after the fact, would have shown up in it. You take your new theory, work out how many events it would have produced passing that old filter, and compare to what the search actually found. If your model predicts many events but the search saw none, then the old search, without ever being rerun, already rules your model out. A result designed to test one idea quietly constrains a second, and a third, long after the data was taken. Picture a fisherman who set his net years ago with a particular fish in mind, checked it, found that fish absent, and recorded the catch. Later, someone wonders about a different fish entirely, one no one was thinking about back then. They do not need a new expedition. They can look at the old net, its exact mesh and where it was set, and reason about whether that different fish, had it been there, would have been caught. The old catch record, honestly kept, answers a question the fisherman never asked. This is why the careful, honest style of the simplified models matters so much. Because those searches describe their filters and results in a clear, general language, stating exactly what they selected and what they found, other physicists can reliably reinterpret them. Whole tools have been built for this, frameworks that take a published analysis and automatically test new models against it. A single, well-documented search can, through recasting, end up constraining dozens of dark matter scenarios its authors never imagined, years after the collisions themselves. Recasting is the buried data idea in one of its purest forms. It says that the answer to a question we have not yet thought to ask may already be sitting inside a result we have already published. The data has been taken, the counting has been done. What is missing is only the new question, the new model, the new angle from which the old, settled result suddenly speaks to something fresh. Nothing new has to be built or run. Someone only has to think to ask. Recasting still relies on having a specific new theory in hand to test against the old result. But what if the right theory is one no one has thought of yet? For that, physicists have begun to reach for a different kind of tool, one that tries to notice the strange without being told in advance what strange looks like. Every search we have described so far shares one quiet feature. It looks for something specific, a monojet with missing momentum, a displaced vertex, a mediator decaying into two jets. In each case, physicists decide in advance what the signal should look like, then go find events that match. This works beautifully when your guess about the signal is right, but it has a built-in weakness, the same weakness that haunts the trigger. If dark matter produces a signature no one imagined, no targeted search will be aimed at it, and it will slip through unnoticed, however carefully the known signatures are hunted. So physicists have begun to develop a fundamentally different approach, one that tries to escape the trap of needing to know the answer in advance. It is called anomaly detection, and it borrows heavily from modern machine learning. The goal is striking in its ambition. Instead of teaching a computer what dark matter looks like, you teach it what ordinary collisions look like in exhaustive detail, and then let it flag anything that does not fit. You do not tell it what to find. You tell it what is normal and ask it to point at whatever is strange. The method rests on a simple insight. We understand ordinary collisions, the standard model background, extremely well. There is an enormous amount of it, and its patterns are familiar. A machine learning system can be trained on this flood of ordinary events until it has a deep, detailed sense of what a normal collision looks like in all its variety. Then you turn it loose on real data, and it watches for events that break the pattern, collisions that sit far outside everything it learned to call normal. It is not matching a template of the signal. It is noticing the absence of normality. Picture a night guard who has walked the same museum for 20 years. He cannot tell you in advance what a thief will look like, what they will wear, or how they will move. But he knows the museum so intimately, every shadow and sound and the way the rooms feel when empty, that the instant something is off, a door ajar that should be shut, a footstep with the wrong rhythm, he feels it, without ever having been shown a picture of this particular thief. Anomaly detection tries to build that kind of guard, one who knows normal so well that the abnormal announces itself, whatever form it takes. The promise of this for dark matter is exactly that it does not depend on our guesses. If the real particle produces a signature outside every theory we have written down, a targeted search will miss it because no one aimed at it. But an anomaly detector in principle might still catch it, because it is not looking for any particular signature. It is looking for anything that does not belong. It is a search that could, at least in hope, find the thing we did not know to look for, the surprise that all our theories failed to predict. The honesty of good science requires naming the limits, and they are real. Anomaly detection is hard. Defining precisely what counts as normal is subtle, and the rare, strange events these systems flag are very often not new physics at all, but some overlooked quirk of the detector, some rare but ordinary process, some flaw in the modelling. Most anomalies turn out to be mundane, and separating a true signal from a mountain of dull surprises is its own deep problem. The method is young, and it has not yet found dark matter. But it points somewhere important, towards searches less bound by our own imagination, more able to catch what we did not expect. And that matters greatly, because after all these decades of searching, in all these clever ways, the plain fact must be faced squarely. Nothing has been found. After decades of searching across 3 continents and 3 strategies, using the most sensitive instruments ever built, here is the honest state of the hunt for dark matter as a particle. No one has caught it. Not the deep underground tanks waiting for a passing particle to strike. Not the telescopes watching for the glow of dark matter annihilating in space. Not the Large Hadron Collider, with all its collisions and all its clever searches. Every one of them so far has returned the same answer, which is no signal, nothing found. This is worth stating plainly and without flinching, because science is only honest when it reports its failures as clearly as its triumphs. The direct detection experiments, the great xenon-filled tanks buried under mountains in Italy and elsewhere, have grown enormously more sensitive over the years, capable of noticing an almost impossibly faint nudge to a nucleus. They have noticed no confirmed dark matter. The indirect searches, watching the centre of our galaxy and beyond for the telltale light of annihilation, have found some tantalising hints, but nothing that held up as a clear signal rather than an ordinary source. And the collider, making and sifting billions of collisions, has produced no confirmed dark matter particle, no mediator, no displaced vertex that survived scrutiny. It would be easy to read that as defeat, but that is not quite what it is, and the distinction matters. A search that finds nothing is not a search that learned nothing. Each experiment that comes up empty has still done something real. It has ruled out possibilities. It has said, with hard-won precision, that dark matter is not here, not with these properties, not in this range of mass and interaction. The space of what dark matter could be is smaller now than it was, not because we found the answer, but because we have carefully eliminated many of the wrong ones. Absence of a signal, measured well, is itself a measurement. Still, the null results carry a real sting, and it falls hardest on the WIMP. Remember the WIMP miracle, the beautiful coincidence that a weakly interacting massive particle would freeze out of the early universe at almost exactly the amount of dark matter we measure. That coincidence made the WIMP the favourite for decades and set the whole experimental program. The searches were built above all to find WIMPs, and the WIMP in its simplest and most natural forms is exactly what the searchers have most firmly failed to find. The particle that theory pointed to most confidently is the one the experiments have most thoroughly not seen. This is a genuinely difficult moment for the field, and the best physicists do not pretend otherwise. An idea can be elegant, well motivated, predicted from 2 independent directions, and still simply be wrong, or at least not right in the form we expected. The universe is under no obligation to match our most beautiful guess. The WIMP is not dead. There are still corners where it could hide, but the easy, natural, miraculous WIMP that a generation expected to find has not appeared, and its silence has grown loud. So the searchers have done their job, even in finding nothing. They have taken the vast open field of possibilities and steadily fenced off large parts of it, marking where dark matter is not. That fencing is real knowledge, painfully earned, and it changes the shape of the problem going forward. To see how much it has changed, and where the classic particle can still be hiding, we have to look at the map the null results have drawn, the shrinking territory where a WIMP could yet remain. The null results are not just an absence, they draw a map. Every search that looked for dark matter and found nothing has fenced off a region of possibility, a range of masses and interaction strengths where, had dark matter lived there with those properties, the experiment would have seen it. Since the experiment saw nothing, dark matter does not live there. Lay all those fenced-off regions side by side, and you get a picture of the shrinking space where the classic particle can still hide. Think of the search as a map with two axes. Along one, the mass of the dark matter particle, from very light to very heavy. Along the other, how strongly it interacts with ordinary matter, from barely at all to relatively firmly. Every point on this map is a possible version of dark matter, a specific mass paired with a specific interaction strength. At the start, before the searches, almost the whole map was open, any point a candidate. The job of the experiments has been to cross off points, to shade in the regions ruled out. The direct detection experiments have shaded in a great swath. Their enormous xenon tanks are most sensitive to dark matter in a certain heavy range, roughly the mass a classic WIMP was expected to have, and interacting at roughly the strength a WIMP was expected to interact. That is precisely the region they have most powerfully excluded. For heavy dark matter interacting at anything like the natural WIMP strength, the searchers have looked hard and found nothing, crossing off exactly the territory where the WIMP was most expected to be. The favourite has been chased out of its favourite home. The collider searches shade in a different part of the map, and this is why they complement the underground tanks so well. The Large Hadron Collider is especially good at reaching low-mass dark matter, lighter particles that the underground detectors struggle to notice, because a light particle striking a nucleus gives too gentle a nudge for the tanks to catch reliably. The collider does not have that problem. It can make light dark matter directly, and notice the missing momentum regardless of how gently the particle would have struck something. So the collider fences off the low-mass regions the direct searchers cannot reach, while the tanks fence off the heavy regions, and together they cover far more of the map than either could alone. But here is the crucial and humbling point. The map is not fully shaded. Large regions remain open, and they are not trivial corners. There is a range of very low masses where dark matter is too light for either the tanks, or in some cases the colliders to catch easily. There is a range where dark matter interacts so weakly that no current experiment is sensitive enough to notice it at all, a particle that simply whispers too softly. And there is an awkward middle zone where the underground tanks lose their grip because of an unavoidable background from neutrinos, the so-called neutrino floor, below which dark matter's rare signal drowns in the constant patter of neutrinos striking the detector. So the WIMP is cornered but not eliminated. Its most natural expected home has been searched and found empty, which is a real and important result. Yet it can still hide in the light, in the faint, in the awkward gaps between what our different instruments can reach. The classic particle is not ruled out. It is squeezed, pushed into the margins of the map, running out of the comfortable middle where it was supposed to live. Faced with that squeeze, many physicists have begun to wonder whether they were looking for the wrong thing all along, and their attention has started to move towards stranger, quieter candidates. When a beautiful idea is searched for exhaustively and does not appear, good scientists do two things at once. They keep checking the last corners where it could still hide, and they start seriously considering that they may have been looking for the wrong thing. Over the past decade, as the classic WIMP has been squeezed into the margins, the second response has grown louder, and the field's attention has begun to shift toward a different family of candidates, ones that are lighter, quieter, and stranger than the WIMP ever was. The first of these is called the axion. It was not invented to explain dark matter at all. It arose in the 1970s to solve a completely separate puzzle in the theory of the strong nuclear force, a puzzle about why that force is so precisely balanced in a way it did not have to be. To fix it, physicists proposed a new, extremely light particle and named it the axion, after a brand of detergent, because it cleaned up the problem. Only later did people realize that this tiny particle, if it existed, could also have been produced in the early universe in vast quantities and would behave exactly like cold dark matter. It was a candidate that fell, unlooked for, out of solving something else, which is the kind of coincidence physicists have learned to respect. The axion is a wholly different beast from the WIMP. Where the WIMP is heavy, the axion is almost unimaginably light, far lighter than even the neutrino. Where the WIMP interacts through the weak nuclear force, the axion interacts even more feebly through a whisper of a coupling to electromagnetism. Because it is so light and so faint, you cannot hunt it the way you hunt a WIMP. Smashing protons together will not make it announce itself. Instead, physicists build entirely different experiments, often involving strong magnetic fields and sensitive resonators, tuned to coax an axion into converting into a faint photon of light. A technique as delicate as listening for a single note in a vast silence. Alongside the axion came other ideas, gathered under the banner of hidden sectors, or dark sectors. The thought is this: our matter is not a single particle, but a rich family, quarks and electrons and neutrinos, and the forces between them, a whole interacting world. Why should dark matter be just one lonely particle? Perhaps it too is a family, a whole hidden sector of particles and forces, mostly sealed off from ours, interacting with our world only through some narrow bridge. In that picture, dark matter is not a single ghost but an entire shadow world, with its own kinds of matter and its own forces, running alongside ours and touching it only faintly. One natural bridge to such a sector is a particle called the dark photon. Just as the ordinary photon carries the electromagnetic force in our world, a dark photon would carry a force in the hidden sector, and it might mix ever so slightly with our ordinary photon, providing the thin channel through which the two worlds touch. Searching for dark photons, and for the light, feebly interacting particles of a hidden sector, has become one of the liveliest frontiers in the field, pursued in smaller, cleverer experiments rather than only in the giant collider. This shift changes what buried data might mean and deepens it. The old searches were built around the WIMP, tuned to its heavy mass and its particular signatures. If the real dark matter is a light, feebly interacting particle from a hidden sector, then it might leave a trace the old searches were never designed to notice. A soft, subtle signature waiting in data taken for entirely different reasons. The answer, if it is there, may be even more deeply buried than we thought, hidden not just in old collisions but under the wrong assumptions about what to look for. The Large Hadron Collider is not finished. In fact, its most productive years are still ahead, and they carry a particular hope for the buried dark matter this story has been circling. The machine is being upgraded into what physicists call the High Luminosity Large Hadron Collider, and the plain meaning of that name is that it will produce collisions at a far greater rate than before, many more crashes packed into every second, and so vastly more data over the years to come. Luminosity in this setting is a measure of how many collisions the machine delivers. Raise the luminosity, and you raise the number of chances for a rare event to occur. The upgrade, expected to begin its physics run in the late 2020s, aims to increase the total number of collisions enormously, so that over its lifetime the high luminosity machine will gather something like 10 times as much data as the original Large Hadron Collider produced in all its runs combined. 10 times as many collisions means 10 times as many chances to make a particle so rare that, until now, we may simply never have produced enough of them to notice. This matters directly for dark matter, and the reason is the tyranny of rarity that has shadowed the whole search. If dark matter is made only in the rarest collisions, then the limit on finding it may not be our cleverness, but our sheer number of tries. A signal too rare to show up in the data we have could show up plainly in 10 times that data, rising at last above the background it was drowned in. More collisions can turn a hint too faint to trust into a signal too clear to deny, simply by giving it more chances to appear. But the deepest promise of the high luminosity era for this story is not only the new data, it is the chance to research the old, armed with everything we have learned, all the techniques that grew up in response to the buried data problem, the data scouting that keeps the soft collisions, the dedicated hunts for displaced vertices, the recasting of finished results, the anomaly detection that looks for the unexpected, the open data that invites the whole world to look. All of these are now maturing. As the new flood arrives, they will be applied not only to it but backward, to the collisions already recorded, asked at last the questions no one thought to ask when the data was fresh. There is a real shift in mindset here, and it is the quiet heart of this whole story. For a long time, the assumption was that finding dark matter meant building a bigger machine and taking new data, that the answer lay in the future collisions we had not yet run. The buried data idea turns that around. It says that some of the answer may already be in hand, sitting in archives at CERN and in the open data available to anyone, waiting not for a new machine but for a new question, a new tool, a new way of looking at collisions we have already caught and kept. Both hopes now run together. The high luminosity machine will pour out an unprecedented ocean of new collisions, and at the same time, the old collisions will be reopened and re-examined with tools that did not exist when they were taken. The future of the search is not only forward into new data, but also backward into old data seen freshly. The place to look is both the ocean coming and the archive already here. Which brings us back at the end to the plain and patient question we began with, and to what it would mean, after all this time, to finally answer it. We began by looking up at a clear night sky, at a few thousand stars and the soft smear of the Milky Way, and by naming the plain surprise that all of it, everything that shines, is the smaller share of what is really there. For every gram of the matter that makes stars and oceans and the hand you raise against the cold, there are more than 5 grams of something dark, something that gives off no light, that we have never held, that we still cannot name. That was the promise of this story, and now we can say honestly where the search stands. We know the dark matter is real. That much is settled from too many directions to doubt. From the racing galaxies Fritz Zwicky weighed in the Coma Cluster, from the flat rotation curves Vera Rubin traced night after night, from the bending of starlight through clusters, from the split mass of the Bullet Cluster, from the faint ripples in the oldest light that Planck measured across the whole sky. Something heavy is out there in great abundance, and it is not made of the protons and neutrons we are made of. On the fact of it, the case is closed. But on what it is, the honest answer is that we still do not know. The favourite candidate, the weakly interacting massive particle that theory pointed to for decades, has been searched for with everything we have, in tanks buried under mountains, in telescopes aimed at the galaxy's heart, in billions upon billions of collisions at the Large Hadron Collider, and it has not appeared. The searches have not failed. They have narrowed the field, fenced off vast regions of possibility, and pushed the classic particle into the margins, but the particle itself has stayed hidden, and this is where the strange, quiet hope of this story lives. The answer may not be waiting only in some future machine or some collision we have not yet run. It may already be here, sitting in data we have already taken, in the recorded collisions on hard drives at CERN, and in the open archives anyone on Earth can download. It may be buried in a signature too soft for the old triggers, in a displaced track the software was told to distrust, in a pattern no one thought to search for because their theory pointed elsewhere. Buried, in that sense, does not mean gone. It means present, but unrecognized, waiting for the right question. That is a different and gentler way to think about discovery. We tend to imagine the great finding as a bolt from the future, a new detector switching on, a fresh collision at last revealing the prize. But the history of this search suggests the answer might come instead from looking again, more carefully, at what we already hold, from a graduate student reopening old data with a new tool, from a machine taught to notice the strange, from an honest result recast to answer a question its authors never asked. The discovery, when it comes, may be less a new sight than a new way of seeing, and if it comes, think about what it would mean. It would mean that the majority of the matter in the universe, the great unseen mass that holds every galaxy together, including our own, had finally been named. It would mean that the fog you and I are drifting through right now, this very moment, as the sun carries the Earth through our galaxy's dark halo, had at last been caught and understood. We are made of the rare stuff, the bright 5%. To find the dark matter would be to finally meet the rest of what we are part of, the vast, patient, invisible majority of the universe we have always lived inside and never once seen. It may be closer than we think. It may already be here, waiting in the data for someone to look again.